Surprisingly, the rotor of an induction motor has no direct connection to the power supply. It is electrically isolated, supported only by bearings, yet can still rotate at high speed. Starting a three-phase induction motor requires careful control. If started incorrectly, it can damage the wiring, starter, connected load, or even the motor itself. Inside the motor, a robust rotor is surrounded by stationary windings, known collectively as the stator. This simple and reliable construction makes induction motors widely used in pumps, fans, compressors, and other industrial machinery. In fact, induction motors account for approximately 70% of all industrial motors, which shows just how important they are. To understand the basic principle, imagine 4 permanent magnets arranged around a fifth magnet at the center, representing the rotor. When an outer magnet moves closer, opposite poles attract and turn the rotor. If the surrounding magnets continue to move in sequence, the rotor follows their magnetic poles and rotates continuously. Of course, physically moving permanent magnets is impractical. Instead, we need an electrical system that automatically creates moving magnetic poles for the rotor to follow. When current flows through a wire, it produces a magnetic field. Winding the wire into a coil strengthens the field, making the coil behave like a permanent magnet while current is flowing. Reversing the direction of the current also reverses the magnetic field and swaps the coil's north and south poles. Manually reversing the current continuously would be impossible, but an AC supply does this automatically. One half cycle is positive and the other is negative, so the current through the coil repeatedly changes direction. If we place the rotor magnet at the center of a single coil, the right-hand rule shows that one side becomes the north pole and the other the south pole. During the negative half cycle, these poles reverse. However, a single coil cannot produce a continuously rotating magnetic field. If the rotor stops in an unfavorable position, the forces may balance and leave it locked in place. To solve this problem, we add windings for 2 more phases, creating a 3-phase system. These sine waves represent a 3-phase AC supply, with the phases labeled R, Y, and B. Each phase is separated from the next by 120 electrical degrees. Within each individual phase, however, the negative half cycle occurs 180 degrees after the corresponding positive half cycle. The same principle applies to all 3 phases. Let us examine the magnetic fields at a particular instant. At this point, the R phase field is 0, while the Y and B phases produce fields of equal magnitude in opposite electrical directions. When these fields combine, they form a single resultant magnetic field. According to the right-hand rule, this side becomes the north pole and the opposite side becomes the south pole. Let us freeze this position for comparison. As the waveforms advance, the R and B phases become positive, while the Y phase remains negative. Their combined field now points in a new direction. Comparing the 2 positions shows that the resultant magnetic field has rotated. As the 3 waveforms progress, the resultant magnetic field continues to rotate around the stator. This is called the rotating magnetic field, or RMF, and it travels at synchronous speed. This principle was fundamental to Nikola Tesla's development of the induction motor. Once magnetic poles are induced in the rotor, it begins to follow the rotating field. In this winding arrangement, the 3 phases collectively produce 1 north pole and 1 south pole. This makes it a 2-pole, 3-phase induction motor. By arranging the stator windings differently, the motor can also be built with 4 or more poles. An actual stator contains a series of slots that hold the windings. This example has 24 slots. During the design process, the number of slots is selected according to the number of phases, the required pole arrangement, and other winding requirements. Now consider the R phase winding. One side of the first coil lies in slot 1. While its return side lies in slot 13, positioned 180 electrical degrees away. The distance between these 2 coil sides is called the coil span. The remaining coils occupy slot 2 and 14, slot 3 and 15, slot 4 and 16, completing the phase winding. The R phase winding occupies 8 slots, 4 forming one pole region and 4 forming the opposite pole region. Their magnetic polarities reverse as the AC current changes direction. The Y phase winding begins 120 electrical degrees from the R phase, at slot 9, while the B phase is positioned a further 120 electrical degrees away. To keep the animation clear, we will show only 1 coil loop for each phase. When connected to a 3-phase supply, these windings produce a rotating magnetic field for the rotor to follow. In an actual induction motor, the rotor contains no permanent magnets. Instead, conductive bars, usually made of aluminum or copper, are joined at both ends by short-circuiting rings. This assembly is known as a squirrel-cage rotor. As the stator's magnetic field rotates past the rotor, its flux cuts across these bars and induces an electromotive force, or EMF, within them. According to Faraday's laws of electromagnetic induction, a changing magnetic flux through a conductor induces an EMF, because the rotor bars form a closed circuit through the end rings. This induced EMF drives current through them. The rotor current then creates its own magnetic field, effectively producing magnetic poles within the rotor. According to Lenz's law, the rotor's induced current creates a magnetic field that opposes the relative motion responsible for producing it. The interaction between the rotor field and the stator's rotating magnetic field generates electromagnetic torque, causing the rotor to turn in the same direction as the RMF. The rotor continually tries to catch the rotating field but can never quite reach it during normal motor operation. The RMF travels at synchronous speed, calculated using synchronous speed equals 120 times frequency divided by the number of poles. Here is the supply frequency and is the number of poles. For a 2-pole motor supplied at 50 Hz, the synchronous speed is 3,000 revolutions per minute. Suppose the rotor is turning at 2,900 RPM, while the magnetic field rotates at 3,000 RPM. The difference of 100 RPM is called the slip speed. In this example, the percentage slip is approximately 3.3%. But what would happen if the rotor reached synchronous speed? With no relative motion between the rotor and the rotating magnetic field, the stator flux would no longer cut across the rotor bars. The induced EMF and rotor current would fall to zero, eliminating the electromagnetic torque. The connected load would then slow the rotor, restoring relative motion between the rotor bars and the RMF. EMF and current would be induced again, producing torque. This is why an induction motor must always operate with some slip when delivering torque. In some cases, an induction motor may hum during starting while the rotor remains locked in position. Why does this happen? If the rotor and stator had matched slot numbers, their teeth would align directly. This creates a low-reluctance magnetic path and may cause the rotor to lock magnetically with the stator, a phenomenon known as clogging. To prevent this, designers use different numbers of rotor and stator slots. The rotor bars are also slightly skewed, reducing cogging, torque pulsations, and magnetic noise while producing smoother rotation. An induction motor also draws a very high current during starting. Initially, the stationary rotor has maximum relative speed with respect to the stator's rotating magnetic field. This induces a large EMF and current in the rotor, causing the stator to draw a high current from the supply. The starting current may reach 5 or 6 times the motor's rated current. If it is not properly controlled, it can cause excessive heating, voltage drop, and stress on the motor windings, cables, starter, and electrical supply system. One way to control the starting current is to use a wound rotor induction motor. Unlike a squirrel-cage rotor, it contains 3-phase windings connected to external resistors through slip rings. Adding resistance to the rotor circuit limits the starting current and provides high starting torque. As the motor accelerates, the resistance is gradually removed, and the rotor windings are eventually short-circuited. However, a wound rotor system is relatively complex and requires additional maintenance. For suitable squirrel-cage motors, a simpler alternative is the star-delta starting method. A typical 3-phase supply may contain 3-phase conductors and a neutral. The voltage measured between any 2 phases is called the line voltage, typically around 400 volts, while the phase voltage is around 230 volts. The motor windings can be connected in either star or delta. In a star connection, one end of each winding is joined to form a common star point, while the other ends are connected to the 3 supply phases. Each winding then receives only the line voltage divided by the square root of 3. This reduces the voltage across each winding and limits the starting current. Once the motor reaches sufficient speed, the windings are switched to delta for normal operation. In a delta connection, the end of each phase winding is connected to the beginning of the next, forming a closed loop with no common star point. Each winding is connected directly across 2 supply lines and therefore receives the full line voltage. On a motor terminal board, the winding terminals are usually labeled U1, V1, and W1 at one end and U2, V2, and W2 at the other. Connecting the links in the correct arrangement forms the delta circuit, allowing the motor to operate at its rated running conditions. You should now have a clear understanding of how a 3-phase induction motor works. If you have any questions, leave them in the comments below. If you enjoyed this video, then please like, subscribe, and hit the bell icon for more engineering insights. Thanks for watching.